Okay. Good morning, everybody. It's a great pleasure to introduce Professor Julio Navarro, who is visiting the IAC through the Fundación Occident Visitor Program. Professor Navarro is a professor in the Department of Physics and Astronomy at the University of Victoria in Canada. So his career began at the University of Cordoba in Argentina and includes postdoctoral training in several places, including Cambridge and Dublin. His academic research focuses on the formation and evolution of galaxies, and of course we all know him also for the very famous Navarro-Franke-White dark matter low density profile. He has published more than 350 research articles, which have been cited more than 75,000 times. He's elected fellow of the National Academy of Sciences of Argentina and the Royal Society of Canada, and he also received awards from the Humboldt Foundation in Germany and the Royal Society in London. And in September 2020, he was included on the list compiled by citation laureates for contributions of magnitude comparable of winners of the Nobel Prize in Physics. So Julio Navarro will stay with us until the 24th of July. He's in the office of 1104, so I hope you will all take the opportunity to talk with him. And then today we'll discuss with us the puzzle significance of ultra-compact satellites of the Milky Way. Thank you.
Okay, thank you. Thanks, Giuseppina, of course, for the invitation, for arranging together with Claudio this month-long visit to the Institute. Of course, it's always a pleasure to be back here. I always start saying that this is like Spain, all the good things about Spain, also good things about Latin America. You speak like us. We say Barcelona, we say Museo de Ciencias. Every time that it says on the tram, Museo de Ciencias, I say, well, I'm almost home. So it's always a pleasure to be here. Today, I mean, I was here last summer, if I remember correctly, or somewhere last year, and I gave a talk, which is very similar to this one, not exactly the same, but it will have a similar context, and I'll try to present an update on things I've said at that time, and a few new things as well. Okay, so for those of you who think I'm going to say exactly the same things, think of another Julio Iglesias, remember that? Yeah, your mother probably liked Julio Iglesias, and he always sings the same things, and people like it. Same thing here, right? I'll say the same thing, and probably, hopefully, you'll like it too. Anyway, so let me get started with a little bit of context for those of you who weren't here last year, and also to fill in a bit of space here. We have a standard paradigm for structure formation in the universe, where we have at least put names to the main mechanisms that we think govern the formation of structure in the universe. And one of the 10 basic tenets of this paradigm is the idea of cold dark matter. Most of the mass in the universe, gravitating mass of the universe, is in a form of matter that we still don't know what it is. There's an ongoing dark matter conference also this few days at the Institute, and I've been happy to go to a few of the talks and discussing exactly what is this puzzle of dark matter. But we have a working model, at least for dark matter, and that is cold dark matter. Basically, the idea is that this is dark matter that fills the universe and is born out of the Big Bang with very small, or very low, or zero, or almost zero velocity dispersion. And therefore, it can cluster on all scales. Okay, so this is because it's cold dark matter and we think it's collisionless, only interacts with other things through gravity, then we can actually solve this as an n-body problem. We know the initial conditions, those are given to us by the microwave background, we know the initial conditions, and we just put this in a computer and see how these fluctuations will evolve through time. And this is what the program, of course, I've been participating in for the last few decades. And the idea is the following: you start with something that's Gaussian, and the universe makes things very non-Gaussian. Gravity makes things very non-Gaussian. Kind of counterintuitive. You say, oh, well, the universe started very, very homogeneous, and as it goes on, it becomes less and less homogeneous. kind of goes goes contrary to what you expect from, usual things of entropies, right? Entropy is supposed to start with things that are very inhomogeneous and make them homogeneous. The universe does it exactly the other way around, okay? And that is one of the puzzles of gravity. Gravity is this funny thing that takes things that are almost homogeneous and makes them inhomogeneous in the case of the universe. So, and we think we understand, at least within this paradigm, more or less the large-scale structure of the universe. And on the large scales, this dark matter, clusters on these kind of funny cosmic web-looking things, like, filaments, sheets that intercross and cross in different places with voids in between. When you go to smaller and smaller scales, and by smaller scales, I mean focusing on things that are denser and denser and denser, we get to a point, especially talking about density, where the densities of the regions that we're looking at, and this is the zoom on one of the densest regions of this particular simulation, you end up with things that are like this. So this kind of honeycomb structure is lost, and there's very dense regions, and where the crossing time there's some days and the crossing time becomes smaller than the age of the universe, the systems virialize. They become equilibrium systems, which are locally basically self-bound. And they look like this. And we call this dark matter halos. Okay? And that's going to be basically one of the basic building blocks of what I'm going to be talking about. We know a few things about these dark matter halos. We know something about their internal structure. We know how many there are as a function of mass. We know also they contain a lot of what we call substructure, which you can see in this figure before. See the halos like punctuated by these little, clumpy things, which is, when you do your dough badly, you end up with these little things like that, clumps. That's more or less what it looks like. These clumps are a result of the hierarchical formation of these objects. You form them by merging together smaller and smaller things, and the relic of these many mergers that accompany the formation process is left behind by these small clumps. Those are basically the central regions of the many subclumps that formed a bigger halo. Okay, so we know quite a bit about these dark matter halos, and I think if I just extrapolate a bit, if the universe had nothing else than cold dark matter, I think this problem would be just solved. We know everything we need to know about dark matter. The problem happens that most of the things we can actually observe, luminous, are other kind of matter. Gravitates also is a minority of matter in the universe, but it is what gives us the beautiful night sky and what makes us tick here in terms of astronomy. We like to understand the luminous universe, not just the dark universe. But we know a lot of things. So let's start with a few things just to set the stage of the kind of things that we need to know. If the dark matter is cold, as I said, it has low velocity dispersion or zero velocity dispersion at the beginning. Therefore, there's no constraints on how dense things can be. Right? So, and the density profiles that come out of this funny aggregation of many clumps together as they virialize look something like this. You have different halos with different masses. And it turned out that they look like this. This is the density profile. So I just go to the center of the halo. It's easy to find the center. And then see how is the density, the mean density changing as a function of distance from the center. And that's plotted here. Distance from the center, density, the log plot. And you see that these are 4 different halos of different masses. And hopefully I won't break anything else today. And you see they actually are very similar. So similar in some sense and different in others, all right? But similar in the sense that the same function fits them all very well. You take this halo, you shift this down a bit and shift to the right and ends up matching this perfectly. That is what we call the self-similarity of this nonlinear structure. You can see also that because the thing is curved, that is not a power law. It is not a power law. It's definitely not a power law. It is more or less isothermal, as we call it. The logarithmic slope is about -2 right here, a shallower -2 and steeper -2, depending on whether you go in or out of the halo. Okay, and that is actually important because it has lots of interesting consequences for that. The other thing that's interesting is that they're cuspy. Okay? They're cusp in the sense that if you do another simulation with better numerical resolution, say, you end up extrapolating this functional form all the way in, but the density doesn't seem to stop anywhere. There's no characteristic upper limit to the density of dark matter, at least in this model of cold dark matter. Okay. The other interesting thing is that all these things are self-similar, as I said, so they all look alike, scaled properly, scaled by their mass, basically. This is, you can guess, this is a very massive system like a galaxy cluster. This is the dwarf galaxy halo. There are more than 5 decades in mass between one and the other. Okay? This is like 10 to the 15 solar masses, this 10 to the 10 or something. As I said, if you scale them properly, they all look alike. They all lie on top of each other, which also means that if you don't scale them, they will look different. In a sense, these are like Planck curves. You know, remember Planck curves? We studied that in the first year of undergraduate physics. The Planck curves, they all look the same, but if you know the temperature, they all look different. Right? Just means that knowing the intensity, in this case, in the case of the Planck curve, or the radiance to be more precise, at a given wavelength, I know the temperature of the system that I'm talking about. If it's of course, if it's the thermal spectrum, the same thing here. This 10 to the 11 solar mass halo, all the 10 to the 11 solar mass halos look the same. They're all the same. So if I measure the density of dark matter inside some region, they will all look the same. I think John Beckham is let's join in and probably welcome. Anyway, so it's all the same. So basically, once you know the dark matter halo or the density of particular radius, you know the halo mass that you're talking about. Okay, so those are interesting things that we'll use in what comes next. The other thing that you can see already is that dark matter halos are quite large. I said this is a 10 to the 10 solar mass halo. It's a small galaxy. It goes to hundreds of kiloparsecs. Okay, so these are very large objects compared to what we usually associate with a galaxy. So a galaxy in this scale, for example, these are 2 dark matter halos. One about 10 to the 12 solar masses, we think is something like the Milky Way. It's a galaxy cluster. They've been rescaled to the radius where the orbit of a particle that goes around in a circle takes about the Hubble time. We call that the virial radius, hoping that inside this radius, there's a chance that things will be in equilibrium because they have at least time to complete one or a couple of orbits inside. This is the scale of the galaxy, more or less. It's the Milky Way. Okay, so the halo goes way out. And the idea here is that galaxies form at the center of the dark matter halos. Okay? Baryons, after all, behave very differently. So the density profiles of galaxies, of course, is not self-similar. They're very, very different from the dark matter. And this segregation, the fact that the luminous component seems to be very, very concentrated towards the center, is the result, we believe, of the fact that baryons can cool, can emit energy. So if we put a bunch of gas there, it will start colliding, exciting electrons, producing photons. As long as the photons can escape, they will lose energy and they will all fall to the middle and start forming a spin in the disk and form galaxies. That's this. So basically, one galaxy, one dark matter halo. That's the part of the paradigm that's quite important. There are in principle no galaxies without dark matter halo. Okay? There may be extreme examples and the ways, well, it's not part of this talk today, but one galaxy, one dark matter halo. Okay? You can see that, I'll tell you in a minute, that the converse is not true. One dark matter halo does not mean one galaxy. And that will be part of the things that we'll be talking about. Okay. Why? Because when you go to the scale of very small galaxies, very faint galaxies, the scale to which I will push the extremes of this talk, then we end up having this dichotomy. Although it's true that every galaxy has a dark matter halo, it is not true that every dark matter halo has a galaxy. And the reason is that we believe that there's a well-defined critical mass below which galaxies cannot form. Okay? I can say, why is that the case? Just to give you a basic idea, if you go to dark matter halos that are very low mass, their velocity, the characteristic velocity, are quite small. Think of a galaxy cluster. Characteristic velocity is thousands of kilometers per second. Think of the galaxy like us. Characteristic velocity is a couple of hundred kilometers per second. you go to a very faint galaxy, the connectivity losses can be tens of kilometers per second. Once you go below 10 kilometers per second, and you have a halo of, say, 10 kilometers per second, and you put gas in it, the collisions between them, especially if the gas is primordial, they will be unable to excite Lyman alpha. To excite Lyman alpha between two neutrally, neutral hydrogen atoms with the electrons at the bottom, you need to collide them at 10 or a bit more kilometers per second. Otherwise, they just behave like billiard balls. So the only way to form galaxies is by cooling gas, and cool gas, I need to make them collide hard enough. And that means 10 kilometers per second. So there's a well-defined limit. Could be 10, could be 5. Things get complicated because hydrogen can become molecular and not atomic. Small potatoes, as we say. Okay, all those are, of course, interesting things, but they don't change the idea that there is a critical halo mass below which you don't form galaxies. The other thing that's interesting about this is that most dwarf galaxies will form in halos of similar mass, okay, regardless of the luminosity. I will make use of this again. The idea comes from this comparison. I told you, one dark matter halo, one galaxy. Okay, so it's good to then compare. Since I know the cluster, I know the abundance of dark matter halos, I know how many dark matter halos in a given volume I have as a function of mass. That is this black line here. There's mass here, numbers here, abundance, number per unit volume. And I can do the same for galaxies. I can just, count galaxies, each with their own mass. Unfortunately, when I talk about dark matter halo, I talk about the halo inside the mass inside the virial radius of the halo. When I talk about a galaxy, I don't know what is the virial mass of the galaxy necessarily. But what I can measure relatively well is the stellar mass, basically the luminosity, and with a few magic tricks, I can turn a luminosity into a stellar mass. I know how many stars I have, and that is relatively well defined. And if I compare the two, I said one galaxy, one dark matter halo, and then I should be able to put, all galaxies inside all the dark matter halos. And the way that this is usually done is by matching them by abundance. It is this number per unit volume. Say if I go to 10 to the 12, I have whatever 10 to the minus 6 of these objects, these very massive galaxies per unit megaparsec cube, say, whatever. Then I have as many of these galaxies as I have with these halos. You see, abundance match them horizontally. So the most natural way of doing this is say, okay, the most massive galaxies live in the most massive halos. And then these galaxies must live in these halos, this mass. These galaxies must live in this halo. These galaxies must live in this halo, etc. When you go to the scale of very dwarf galaxies, low mass galaxies, because this becomes much flatter than this one, then you have this pileup of all the galaxies, the dwarf galaxies, on halos of very similar mass. Okay, just to visualize that, imagine that this was exactly flat. Okay, that's the Schechter function. Imagine it was exactly flat. If it's exactly flat, then all these galaxies will belong to halos of very similar mass. Okay, so that is what this introduction basically of a threshold halo mass leads to. And it is actually the only way to make sense of this inside this paradigm. So it's actually a very strong prediction. It tells you that every dwarf galaxy from 10 to the 7 solar masses and stars to 0, to whatever you want, live in halos of very similar mass. That's a very strong prediction, right? Something that we should be able to test and rule out. When you do simulations, these things, of course, are come out reasonably well. This is a simulation now result. This is halo mass again, stellar mass in blue. You can see how the stellar mass goes to basically 0 below a certain mass. That's the critical mass. Below here, there are no galaxies. Above here, there are galaxies, and the transition is actually quite sharp. Okay, and you can see also here, because this is vertical, that all these galaxies live in halos of the same mass. Okay, so it's kind of that's quite important. Because why is that important? Remember what I told you at the beginning. Halos of a given mass, they all look alike. They're all basically the same. Give or take a few secondary corrections, but they all look the same. Okay? Last time I was here, I told you about what happens to systems that are below this halo. They actually have no stars. Okay, and I told you also about perhaps a system that is down over here in terms of stellar mass. You know, I'll mention a little bit of an update on that today as well. What's also interesting is that when you go to low dwarf galaxies, of course, now our knowledge of these very dwarf galaxies is very limited because they're very faint, so we can't observe them very far. Okay? So most of our knowledge of the dwarfest, maybe the most dwarf, whatever, part of the luminosity function comes from our local universe, basically our Milky Way and perhaps the local group, and not much further beyond. And they look like this, all of them. Should not. I told you that, you know, well, in Milky Way, you see the gas comes, spins, forms the disk. And apparently, when you go to dwarfs, it's not the case. Okay? Dwarfs look like this, look like a ball of stars. Okay, that's just each star goes around, perhaps on orbit of a given electricity, all with different orbital planes. Therefore, the mean rotation of this system is not very important. The only thing that is important dynamically is the velocity dispersion. How different is one velocity relative to the other, and perhaps how far away they are from the center. But you know, it's basically a bunch of stars, individual stars, resolved into individual stars. Now, when I have this, of course, I can take a spectrograph and measure individual velocities, take a spectrum of individual stars and measure the velocity of dispersion. And a star like this one, this galaxy like this one, this is a nice galaxy. This looks very nice. This is the Fornax dwarf Freudel, one of the biggest ones. It's about 10 to the 7 solar masses in stars. I can do this for thousands of stars, right? And construct and measure things very well. For example, I can measure very well what is the radius that contains half the stars. It's well defined. Half the stars are within this radius. That's very well measured. I can also measure, once I have thousands of velocities, very well the velocity dispersion. I measure velocity dispersion and the size, and then I can estimate the total mass. Okay, take velocity dispersion, like we do always in astronomy, take velocity, square it, multiply by size, that gives you the mass. We do this for the mass of the sun, so I take the velocity of the Earth, square it, multiply the distance to the Earth sun, and that gives me the mass of the sun. Okay? Very simple. So those are really robust measurements. Now, I can turn this around a little bit and say, well, instead of measuring the total mass, what if I'm interested in the total density of matter? Why? Because what happens is that when you measure the total mass of this object inside this radius, ends up being much, much greater than the mass of the stars. Basically, you're measuring the total mass of this object inside that radius, but you're measuring a mass of dark matter. These are dark matter dominated systems. And the fainter you go, the more dark matter dominated they become. So that's an interesting thing, because what can I do? Well, I told you all these dwarf galaxies live in the same halo. So they all should have the same density profile. And here's a measurement. For this galaxy, I know how much mass, there is inside this radius. I can take the mass divided by the volume, I get a mean density. That's the total density of dark matter inside that radius. Okay? Now, what's interesting, if I go to another galaxy that is perhaps smaller, then I can measure to the same. And if the galaxy is smaller, I'll have an estimate of the density of dark matter inside a different radius of the same halo. Okay? And if I have many, many galaxies of different sizes, then I can reconstruct one by one the mean density profile of a dark matter halo where all of these galaxies belong. Okay, so that's what we like to do. So that's what we're actually able to do. Why do we want to do this? Because, you know, there are alternative models for dark matter. Cold dark matter is not the only game in town. There are other, for example, you may think, oh, well, maybe the dark matter is not collisionless. There are collisions between particles. But collisions between particles, what happens is that now you can transfer energy from one part of the system to another. And this cuspy profile that I mentioned will change because of this energy transfer effect. Okay? And you end up having things like this. For example, the density should become constant, for example, under the usual parameters or the most natural parameters, if you want, for stuff interacting in dark matter. And that's quite different from this. So if this is true, it tells you, look, oh, any halo, any galaxy that is smaller than this radius, and say a couple of kiloparsecs, they should all have the same density. Another idea that goes around is the idea that the dark matter maybe is a collisionless particle, but it's of such low mass that their de Broglie wavelength can be of the size of a galaxy. When that happens, the thing behaves like a quantum, gravity field, and you end up having a soliton, a zeroth order, density at the center. Depends basically only on the total mass of the particle. If the particle is very, very small, like 10 to the minus 22 EV, right? When you go to you go to the Museo de las Ciencias and talk to people who are playing around with things, they talk about 100 GeV particles, 10 GeV particles. Here's 10 to the minus 22 EV. So there's like, 40, 50, whatever decades difference. Then this thing becomes this quantum behavior form becomes almost macroscopic. And you can see this on scales of kiloparsecs. So you end up having a maximum density that is imposed by this quantum limit, if you want, like almost the degeneracy pressure applied to dark matter. And you have also constant densities, okay, constant densities. And if you choose the numbers properly, you end up with constant densities which are the order of what you want to apply to some of these galaxies. Basically, they're quite different. Okay? So what we want to do is apply this method, this idea I told you. Take many, many dwarf galaxies, measure the densities, and plot density versus radius. Okay? It should be all the same below a certain radius if they are self-interacting or fuzzy dark matter, and they should continue going up if they are cold dark matter. Well, actually, we can do this. We have these measurements for a bunch of galaxies, and this is what you find. This is the prediction. This is mean density, radius. This is the prediction from cold dark matter. And these are all the satellites in the local group. Okay? So all the local universe satellites are there. You see, the main trend that I was telling you about actually holds as I make this is one satellite, one different galaxy. Okay? As the satellites become smaller, the trend is they become denser. Okay? And they become denser more or less following the same line. See, if I had halos which are very, very different masses, they would actually be very different. A low mass halo would be like this. A very massive halo would be like that. But a halo of about that threshold looks like this gray band. So miraculously, between quotes, things more or less fit. And there's nothing in this model that has been trained to match this. Right? This is a completely post facto result. That actually, if you go to the early plot that I showed you of dark matter halos, that was done in 1996. We didn't even know that the satellites existed then. Right? So this has not been trained in any way, and those numbers haven't changed. Cold dark matter has been predicting the same densities, if you want, for a long, long time. So this, if you want, is a fairly strong evidence for something like cold dark matter. To give you an idea of what look at the numbers that these models predict. Mean density is central density of 10 to the 7, 3 times 10 to the 7. Okay? And the numbers you hear, this is 10 to the 7 here. 10 to the 8, 10 to the 9. These are much denser. These are not like, factor 2 here or there. These are decades denser than the objects that we predict from an alternative model of dark matter. Okay, so what we like to do is find, of course, you can see this I prepared this from the plot. We would like to have smaller satellites because the prediction is very clear. The smaller the satellite, the denser it should become. All right, that's the prediction. Is it true? Well, I guess that's where data come in, right? So we like to find smaller satellites. Of course, now they're looking at systems that are so faint that are very, very hard to find, not even, beyond 100 kiloparsecs. Actually, we're lucky if we can find them within tens of kiloparsecs from us. So we're looking at really at the Milky Way. And that all this, new data that I'll show you, or new older combination comes from Milky Way. So we're looking, this is the Milky Way, of course, from the beautiful Gaia satellite picture, the LMC, the SMC, and these little dots you see over here are satellite galaxies. Okay, so we'd like to find more satellite galaxies, especially very faint and very small ones. Why? Well, because, at least in cold dark matter, we can count how many of these little clumps there were. Remember the clump as the substructure of the halos? That's where the satellites should live. So we can count them. And we know how many there should be above the threshold from galaxies. So we know, having a good idea, how many satellites we expect. It turns out we expect about, 200 satellites in total. It's not an infinite number of satellites, only a few hundred. And if you compare now more detailed models, I guess, you can see that the most massive satellites can be reproduced fairly well. This is the cumulative luminosity function of satellites, but there is a prediction that there should be lots of faint objects that are still missing, okay? So we're looking for these objects. They're faint, hopefully they're small, right? So they actually will help us in our density plots, and we look to find them. And the way to find them is following. If you have a bunch of stars more or less of the same age, and more or less the same distance, and with an initial mass function that is reasonable, yes, we find that this is what you see. This is a star cluster, all the stars are the same distance. If we plot color, sort of a ratio of fluxes between two bands and magnitude, how bright they appear, they have this funny little curvy thing, right? Which we call the CMD, of course. And it's all the same. All the satellites should have the same thing. Of course, if it's fainter, it will be fewer points. If it's farther, it will be fainter. So the whole pattern will shift down or shift up depending on the distance. Yeah. So that's what we do. We look for curvy things in a color magnitude space of a big survey, and we start finding things. Okay, so this is one example. This is from William Willman 1. This is one satellite. You can see that can be quite faint, right? So these things have to be confirmed. This is another satellite. Actually, there is a satellite there. They're almost impossible to find when you go fainter by eye. You have to find them really statistically and then confirm them. It's actually an obvious one. This is actually a fairly luminous one compared to the ones I'm talking about. When you have a bunch of them, you start finding them, okay? And then you have this, can plot now all the satellites of the Milky Way that we know. Okay, so this is the size of the satellites, and this is the luminosity of the satellite. I know the distance. Remember, I know the distance because I know when this curvy thing has to turn off, as we call it in astronomy. And it's interesting because it seems that if you look at systems that are in the Milky Way halo, they're not part of the disk. The disk is full of stuff. And they're not very close to the center either, where things are complicated. Then you find that this is what they look like. Okay? Size, again, and distance. There are these things that are painted red. Those are your well-known globular clusters, small objects of a given, reasonably luminous objects, but very, very small. That's why they're easy to find, and people study them for hundreds of years, I guess. And there are these things which are much more diffuse, they're bigger, but they actually are comparable distance. So this is the kind of objects we're talking about. We're talking about objects that are as faint as a globular star cluster, or even fainter. These are plenty blue because at least, for the data that we have available, they have evidence for dark matter. Okay? In other words, the velocity dispersion is too large compared to what you expect for a self-bound object with only stars in it. The systems have no gas. There's no detections of H1, molecular gas. There's nothing like that. Maybe detections from gamma rays. Actually, there are no detections of gamma rays that people trust, and that's something that people are talking about in this meeting that is going on here. But they are there. So clearly our satellites that are there, then we know the distance, we know how bright they are, and apparently they have evidence for dark matter. Giuseppina doesn't believe a lot of these things, because a lot of these velocity dispersions are dubious, and I totally, if the data change, I change my mind. So that's how I do it. So, but for now, allow me to continue. Now you can find these things, in big surveys, you can find lots of these things. And there's a bunch of things like this that people have found that are very compact, they're as compact as globular clusters, but they're much fainter. Typical globular clusters are, 10 to the 4, 10 to the 5 solar masses. These are a lot fainter. Okay, look, this goes to 2.5 here. Do you remember your astronomy 100? What is the magnitude of the sun? What is the absolute magnitude of the sun? I wouldn't embarrass you. 5. Okay, 5. That's the number you want to remember. 5. If this was gone to 5, we'll go to the luminosity of one sun. Okay? 2.5 means a luminosity of 10, 20 suns. This is the faintest satellite that we've ever discovered. This is the Ursa Major 3 or Unions 1 satellite that I talked about last year. I want to give you a little update on that. Why? Because it's important. See, if this was a dark matter dominated object that has dark matter, then it's very small. You see, it's 2 parsecs, 3 parsecs. I can put it on my density plot and say, wow, does it look like cold dark matter or not? Does it look like what the prediction was or not? And there's been quite a bit of debate. But let me talk about this population. This is actually what I'm talking about in the title of the talk. These are the ultra faint compact satellites. Okay? You can see why they're ultra faint. They're really, really faint. And why they're compact. They're as compact as global clusters. Scales of parsecs. Okay, so where are they? Where are they? We'd like to know. Let's look at where they live. They've been found in the galactic halo. So in that sense, they're distributed, if you want. Look at the magentas. I forget what the colors are. I think it's magenta. Call it magenta. The magenta things are in the Milky Way halo because this is where we've looked for them, so it's perhaps not super surprising. But they're quite different. They're quite different from the globular clusters. You see, globular clusters are all the majority of them are pretty close to the center of the galaxy. After all, that is how we discovered that we are not in the center of the galaxy, because all the globular clusters are over there in the direction of Sagittarius. Okay? Harlow Shapley taught us that, and you can see it's pretty obviously. It's the red things of globular clusters. Also, the distances of globular clusters. This is distance to the sun. It doesn't matter. Distance to the center of Milky Way be similar. You see, there are things that are very close to the center of the galaxy. These are globular clusters. And most dwarf galaxies and these funny objects, these ultra-faint compact objects, which are in color in this plot, taken from Will Cerny's recent work, they are at distances comparable to the dwarf galaxies rather than globular clusters. But this is, not that convincing. What you really want is a velocity dispersion. Because why? Because with the velocity dispersion, you can, again, take velocity dispersion, you square it, multiply by the size, and that gives you mass. And I compare that with the mass of stars. When I do this for globular clusters, this is mass versus mass. Total mass versus mass in stars. You see, globular clusters are all in this one-to-one line, defined in some way. And the dwarf galaxies are all way above. They're dark matter-dominated objects. They have a lot more mass than there is mass in stars. Okay? So an object, for example, like this very, very faint object, the faintest object that we know is Ursa Major 3. If we was a globular cluster, we'd have velocity dispersion that would put this in this, right? It has a 16 solar mass total mass and a 16 solar mass in stars. It means that velocity dispersion of this object should be of the order of 50 meters per second. Meters, right? So basically all this stuff, when I measure this with any reasonable spectrograph, I'll see that they all have exactly the same rate of velocity. Okay. On the other hand, if it was a galaxy, it would have enough dark matter to be at least on this, maybe on much higher velocity dispersions. Okay, so that's what we like to do. That's why we want a velocity dispersion of this. This was the results that I showed you last year. We believe that this is a real system of average velocities. There are many stars on the same color-magnetic diagram with similar velocities. So this is truly a system. And we thought at the time that the velocity dispersion was well resolved. Actually, you can actually measure this, and it was about a couple of kilometers per second. Okay, very different than the 50 meters per second. Now, it turns out that there's been newer data, actually not new stars. There's the same stars with newer data. This is data taken with a medium resolution spectrograph. So the individual uncertainty in the measurement is about a kilometer per second. the velocity dispersions you measure are about 1 kilometer per second. So you can see this is quite hard. And on top of that, there's the issue that Josefina always tells me, what about binaries? What are binaries? What if some of these velocities you're measuring, of course, the velocity of the star, but it doesn't measure the velocity of the star inside the galaxy. It measures the velocity of the star around another little thing. Okay. Remember, we orbit around the sun, and we move at 30 kilometers per second. 30 kilometers per second, right? So if you're reasonably close to another star, motions you expect are very, very high. And we try to measure things at 1 kilometer per second. So binaries are a problem unless you have many repeat observations, blah, blah, blah. Josefina will tell us all about tomorrow in the morning, which I hope I can hear. Josefina, who scheduled you at 9 in the morning on a Friday after a social dinner? I think, can we do this on Zoom like we used to do in the good old days of the pandemic? I can do it from my bed or something. But anyway, I'll do my best. But anyway, so better measurements of the same stars, and now the velocity dispersion is apparently unresolved, is what we call it. So in other words, the probability that it might be quite small is non-negligible. There's an upper limit now of about 2.5 kilometers per second. So it can be anything below 2.5 kilometers per second, but there's no clear detections. In that sense, we still don't know if this system has dark matter or not. The reason why I was convinced, I'm still convinced that this has dark matter, is that if it didn't have dark matter, we know its mean density. And it's so faint that we found it only because it's very close to us. If it's close to us, we are 8 kiloparsecs from the center of the galaxy. This thing is orbiting at about 8-10 kiloparsecs from the center of the galaxy. The mean density of the galaxy is huge. Right? How do you know that? We know that because we go around at 200 kilometers per second to go around in a circle. So you have to be very, very dense to survive as a bound object at this distance. And so we use that and say the density of this system needs to be big enough or high to survive the galaxy. And we know the orbit, of course, we know the velocities, etc. And we can do this quantitatively. And the answer is that without some dark matter or of some kind, doesn't mean that dark matter is called dark matter, but without some dark matter, some more matter, this cannot survive. So I think now the bleeding edge of these discussions is whether the dark matter is maybe in an intermediate mass black hole, maybe it's in stellar remnants. So it's a bit of a free for all there in the literature. But anyway, this is what it looks like in our density radius plot. This is if you have no dark matter, okay? Just the stars and nothing else. You see, this is the density of the galaxy at that distance. You can't survive there. You need to be much denser than the galaxy. You want an example? Why is the moon attached to us? The moon is attached to us because the mean density inside the radius, the distance to the moon, to the Earth, is much higher than the mean density of the sun inside the radius of the moon. Right? The moon orbits in about a month. We orbit in 12 months. Okay, so has to be denser. Density, remember, is the inverse of time. So to remain attached to us, it needs to orbit around faster than we go around. So it has to be denser than that. So that's the same idea here. If you have something that comparable densities, then the time it takes for one star to go around the object will be the same as it takes the object to go around the galaxy, and that would be lost. Okay? So it has to be something here, whether it is called dark matter, whether the densities are, this is the upper limit now, where densities are as high as that, or perhaps somewhere around there, that is still under debate, I guess. Okay. Interestingly, there have been other objects like this ultra faint, the compact satellites, for which Will Cerny and company and collaborators in Yale, Chicago, mainly in Toronto, they've been able to measure velocities for a bunch of stars. There's always, the number of stars is fairly limited, but for some of these galaxies, they've been able to measure velocities which of enough quality, I guess, that when you put them through the whole this Bayesian machinery, you end up convincing yourself that there's a 95% chance that you can rule out the velocities that you expect from having no dark matter. So this is the gray part here. You see the gray thing here? That is the prediction if it has no dark matter. And the velocities are upper limits in many cases, but in some cases they're not. You see, there are no arrow. This one, for example, this one, etc. So there are velocities. Of course, more data and binaries, Jasmina, I heard you, can change this a bit, but, allow me to, you have to, say, let's believe the data for a while. Because the good thing of being an astronomer is that you have prejudice, right? So so you want to be a good astronomer, you have to have strong prejudices. If you want to be a great astronomer, you have to be able to change your prejudices when the data forces you to. But anyway, but if you take these values, then this is what you get, right? There are some upper limits here, as you can see, and these are the three for which there are claimed velocity dispersions that are non-zero or not stellar. And you see that they're all more or less, where we expect them to be. Very small objects, much denser than the rest of the satellites. Can this be accommodated with other models of dark matter? Maybe. Okay, we can always change parameters in the models to get something, but it is interesting that I haven't changed any parameters for this. You can go to the NFW paper, 1996, and plot the density profile of a dwarf galaxy. It is that one, the gray one. So nothing's been changed here. The idea here is that basically halos are cuspy. See, they're very dense in the center. So I can go and, if I manage somehow to form tens of 100 stars very close to the center, they have to be very dense. And because they're very dense, they can survive in these very extreme orbits. And so anyway, so that's more or less where the story is relative to, and the update I want to give you on that. I give a couple of things that are a bit newer now, or in particular one new thing that I'll tell you. I can't tell you everything about it because it's embargoed. I learned that if you say it's embargoed, people say, oh, wow, it must be very important. I'm not sure it's that important, but anyway, we say embargo and people pay attention. So I'll tell you about something that's still embargoed, it's just submitted to Science, and we haven't heard from the editors yet, but anyway. The idea is the following. Okay, imagine we cannot measure velocity dispersion. It's too hard, there are too few stars, errors are big, whatever. Is there any other way of doing this to differentiate these galaxies from star clusters? At least globulars, or actually most star clusters that we know of, have one characteristic. They're made not like galaxies. They're not made of, what is a bona fide galaxy? What is something like the Milky Way? It's a halo, gas falls in, the gas only is hydrogen and helium to begin with, you start forming stars, the stars eject the metals, and the metals start polluting things, and therefore you have, a track record, if you want, of this enrichment process. You have some very, very metal poor stars, some, stars that are more metal rich, and some progression between the two. That is a bona fide galaxy. The galaxy started from zero metallicity and built its way up to the metallicity it has today through an self-enrichment process. That doesn't happen to globular clusters. When you take globular clusters, you measure velocity dispersion with some exceptions, the stars of all the stars, and they have the same iron metallicity. Okay? This is the iron metallicity distribution of globular clusters in the Milky Way. And this I will call this some dispersion. No, there's no dispersion. This is a dispersion between clusters. Each cluster has all the same metallicity. They're all in the same bin. All the stars in one cluster in the same bin. The exceptions are, of course, Terzan 5, M54, and Omega Cen, okay, which we believe are different things. There's a dense star clusters are not globular clusters. You say, well, what is the difference? What happens when you go to a dwarf galaxy? Well, go to a dwarf galaxy, I told you we have few stars to begin with. Few stars are bright enough to take spectra. But for those that we can, we have things like this. This is CanVen1 distribution, individual metallicities in iron. And you can see there is a very strong dispersion. And you have this tail of low metallicity. So the idea here is that you start with zero metallicity and you start enriching yourself to the mean metallicity of the galaxy, which in this case is -2 or something. So you want to see this tail, you want to hit this dispersion in metallicity to convince yourself that you're talking about a system that has progress from 0 to whatever melistic has. Unfortunately, when you go to this ultra faint, this Kanban one is a pretty massive one in this game. You go to ultra faints, you can only do this for a few stars. Sometimes, you only have 2 stars. This in Carina 3 or something, I forget. You have 2 stars, but the 2 have fairly different melistic. And say, wow, that's enough. This is a dwarf galaxy. We can see this is, there's a lot of potential for mishaps here. This is Carina 2. We can see each of these little bars 1 star. Okay, so 1 star or 2 stars. But this is the way you can do it. So you want really to have a measurement of this, and also a proof. And I like proof. You want to proof that these ultra faints, which only have hundreds of stars, really started in a dark matter halo with pristine gas, with 0 metallicity gas. What is the only proof that we have of this? Finding stars which are metal free, all right? They have no heavy elements. Those stars, we've been looking for them for years, including here, I guess, and we haven't found. Yes, so we haven't found many of them. There's only 1 star in the whole Milky Way that has no iron detected. 1 star of the millions and millions of stars that we studied. 1 star. And that was found about 10, 12 years ago. 1 star has no iron in its lines. Well, I'll present you the second star. And it's not in the Milky Way. It's in a dwarf galaxy. A star that has no iron. So in this plot, it will be a minus infinity. Okay? Well, we don't know. So it's an upper limit. Of course, it could be very small. But, so I'll present that star. This is the Milky Way is a galaxy. So we have the tail below metallicity. You see, the tail below metallicity, metal poor stars. There are stars in the Milky Way that are a halo that are as metal poor as -5, -6 almost. But they all have metals. They all have iron. These are the ones that detected irons, right? The star that I was telling you about is below 10 to -6 or -7. So I'll present you the second star like that. And this again embargoed, so it must be very important. Okay, so this is the galaxy. I can't tell you which galaxy it is, unfortunately. So I have to get a bit of secrets here. Maybe by the end of my stay here, paper will either be rejected or accepted, in which case I can tell you more details. But this is one of these are 2 galaxies here. There's 1 dwarf galaxy, another dwarf galaxy here. This is work by Anya Dovgal, Kim Ben, Al McConaughey, and a bunch of us who do just overawed by their their data and their savviness. As I said, there's only 1 star known in the Milky Way. This was discovered by Keller in 2014 with no iron. So this is the Colomagno diagram of that galaxy. The red ones are the ones in our survey. The other ones are data from the literature. We targeted all the stars in this galaxy that had no high resolution spectroscopy already published, to convince ourselves that this is a member of this dwarf galaxy. You can see it's really close to the middle of the galaxy, has a velocity of 475 kilometers per second, which is incredibly different from any velocity of the halo stars in that direction. So clearly this is really a star in that galaxy, so there's absolutely no doubt. And this is what the spectrum looked like. Okay. This is 4 stars in the same galaxy, ordered by metallicity, -1.73, -4, and this has less than -6. They said there are no detected iron lines. And you can see how it changes, right? So all these lines here on this very small part of the spectrum, all these lines are non-existent in this galaxy. Okay. Why can we do this? And do this because there's this beautiful spectrograph in the Gemini South Telescope in Chile, which is built in Victoria, and it's called GHOST, and which allows for its high-resolution spectra, beautiful high-resolution spectra to be taken. Give you an idea, this is 50 angstroms, right, in width. Okay. So this is 70,000 R, for whatever those of you spectroscopic in mind. You see all these lines disappear. There's basically nothing. Of course, there's not. There is something. Of course, there's hydrogen, thankfully. And there is carbon. Okay, there's a lot of carbon. There's also, there's no calcium, or at least no sign of calcium. This is a calcium triplet. The calcium triplet is one of, there's a calcium H and K line and a calcium triplet. Those are the two things that first you look at in the spectrum. There's none of that. This is calcium. This is the strongest line in the calcium triplet. You see, it's obvious up to -4. It's incredibly obvious. And you don't have anything on this galaxy either. So this is the distribution of metallicities for the stars in the same galaxy, and this is less than -7. You see, we've been able to, in my mind, find this tail, the tail towards zero metallicity stars that tell us that these ultra-faint, and by extrapolation, many of the ultra-faints are really real galaxies. They really started with a dark matter halo, with gas that started with zero metallicity. Those of you who are aficionados of this, we can measure carbon, nitrogen, sodium, and magnesium. Okay, and I'll skip this a little bit in the interest of time. One of the things that people play around when they find the stars, they're believed to have been, polluted by perhaps a single supernova event that happened, or the first supernova event. They're not pristine stars. They do have carbon. They do have, but they don't have iron. Right? So they have quite a bit of carbon compared to oxygen, to hydrogen. You see, this is carbon abundance. The red line are this new star. The blue lines are this other star, the Keller star, which is in the galactic halo. And the main difference here is that, they're actually very similar. And the other main difference is that one is in the galactic halo, and the other one is in this dwarf galaxy. You see, they actually look very similar. They have no iron, have only upper limits in iron, or here have only upper limits in calcium, and there are light elements which are, in patterns that are, sometimes difficult to understand. For example, why does it have as much carbon as nitrogen is not completely obvious. After all, carbon is, is an alpha element, nitrogen is not. So it tells you a lot about this thing. So you can try to match this with models of a single supernova or a single, fast rotating star, and you can do reasonably well. And the main story that comes out of this is that for some reason, the first supernovae, both in presumably the galactic halo, but also in this dwarf galaxy, are similar. They're able to put out light elements, carbon, nitrogen, magnesium, but not iron peak elements. And the idea is going to be in the communities that the first supernova, for whatever reason, they're weak. They only pushed out the outer parts of the core collapse. They explode, but don't explode very fast. And therefore, the inner parts, the parts where the iron is, the iron peak elements will just fall back and go into the black hole and to never be seen again. And the part that goes out and pollutes the rest, out of which this star presumably formed, is enriched in carbon, magnesium, etc. Okay, you see, it's actually quite different than other models. Like a very popular model is appealing to parent stability supernovae. The star is very, very massive and primordial. Then you have parent stability supernovae because very more than 100 solar masses. You collapse not because the core collapses, you collapse because the star is unstable to the formation of electron-positron pairs. In the form of these things, the pressure disappears and the star basically collapses, or actually detonates in just one go. But it produces a pattern of elements which is very, very different from this. It produces lots of iron, lots of odd and even effects and things like that. You can see they're don't match at all what you observe here. So, at least we have two stars telling us that the first supernovae were weak. And what that means exactly for the whole game of, nucleosynthesis in individual stars community is actually quite interesting, still to be. I mean, I had some other things to tell you, but what time is it? This I should be finishing. Okay, that's good. Definitely I want to tell you is another something like this, but I can tell you about it some other time. How about that? So we'll end here. I'll put my conclusions here, and I'll thank you. Thank you for your attention.
Thank you, Julio, for your excellent talk. I guess we have time for some quick questions. Let's see if some hands already.
Thanks, Julio, for a very
nice talk, full of many things. So going back to a plot that you showed already last year, and now you showed again with new data, the density versus half-life radius. I don't know if you can put it back again. Now you got new ultra-compact dwarfs, okay, to add to the
This one?
low, yes. So I'm a little bit puzzled because if you take them all together, this data, they do not seem to follow the slope predicted by an NFW. They seem much steeper for UFC and a little bit less dense for, particularly for the dwarfs that are the most luminous, where we perhaps expect some feedback to be happening. So I was wondering if you have any thought about that, or because if I just do a fit, I mean, I'm sure you did, but if you do a fit through those points.
Fit by eye. Yeah, no, I know.
Fit by eye. If I do a fit by eye.
Chi by eye it's called. Yeah. Anyway, I didn't put any error bars here. And so I could put the error bars, it's just too much stuff here. I only put otherwise the arrow, you won't see the arrow. These are all upper limits because they could be much lower. And these error bars here are at least as big as this error bar here. So I wouldn't read too much into it. Although, you may be tempted to say, well, they're denser than NFW, and therefore there must be something
I'm
else.
more worried about the faint time where the error bar are really tiny and neither of them coincides with the aesthetic.
Oh, here, you mean?
NFW.
Oh, that's a different thing altogether. Okay, sorry. We were talking about
The question was both. Yeah.
both. Okay. Here, I just would read that the fact that there's zero third idea, the smaller things are denser, seems to be correct. How dense? I think we need a bit more precise measurements. Okay. Now, these things over here, why are they below this line? That's quite interesting. The main idea here, which I think is reasonably correct in some cases, is that the reason why these things appear to be less dense than you predict is because they're being disturbed by the tidal field of the Milky Way. Basically, you have this halo of dark matter, you have the stars in the center, you put this in an orbit inside, and you start losing most of the dark matter halo. That affects the mean density in the region where the stars live, and it will lower the density. After all, we're measuring the density of dark matter. In cases that are extreme, we may think that we're measuring, the mean density of the remnant, but we're actually measuring just the disruption of the system, and we're measuring basically a piece of a stellar stream. That's the idea, at least behind the interpretation of these very extreme objects like Crater 2, for example, which are very, very low density for their size and their luminosity. Okay, and it is, I think, proven that both Crater 2 and Antler 2, they actually have very prominent stellar tails. Now, this needs to be done a bit better. And I think we need to come up with models that are a bit better and that that explain the results as they are. But the idea is not crazy, I would say. But all of these things are food for thought and further work. And the same idea with this one. So there are other things here. Andromeda 2, version 12 is here, although the error bars are huge, and there are many things that are below. So the main idea here is that all of those things were formed inside this gray line, and they've been brought down by tides. Why haven't these been brought down by tides? It's just because you're such high densities that although you may lose all of the dark matter halo, you don't lose it from the very, very, very center. Okay, so these are more affected by tides, which are larger and lower density than these ones. But the idea kind of hangs together. Now, in details, we can worry about it. I think we do worry about it, and there's lots to be learned yet.
Thank you.
Yeah, so Ariana has made the first question that I wanted to ask you, so I will do the second. So this is all based on the idea that galaxies are born on the same dark matter halo. So you are not allowing to plot here different dark matter halos predictions, like instead of 10, I don't know. I don't know which line is that, 10 to the 9 dark matter halo, or
this is a 10 to the 9, a couple of times 10 to the 9 plus or minus, in some scattering concentration and in redshift of formation as well. For those of you who know what, that's why it's not a single line, but there's some width in this.
Yeah. How secure are we about that prediction? Because, for example, what happens if some of these galaxies are born in more massive or less massive halos than the ones that you are assuming? So that would be fitting as well? Or so that's my first question, and then just to finish, the second question is, You mentioned that this is somehow against alternative dark matter model, like self-interacting dark models, but do we have also a similar prediction? So do we expect also that if self-interacting dark matter models or in fuzzy dark matter models, the galaxies that were born below some dark matter mass would be also living in the same dark matter halo?
You asked several questions,
Yeah, that's right.
Nacho, here, so I guess I'll try to give you a few answers. Perhaps not all of them, but the main idea, if dark matter halo where these things live was much lower masses, say 10 to the 7 solar masses, then the densities would be around here. But this would be a parallel line to this one, but it would be around here. So the fact that these things are so dense, it tells you right away that things have to be, the halos where they form, they have to be reasonably massive. Okay? Remember what I told you, halos don't cross, right? So a massive halo, a more massive halo is denser than any low mass halo at all radii. Okay? So the fact that it's dense tells you the halo is massive. How dense, how massive, that we can discuss a bit more. But it tells us it cannot be a 10 to the 6 solar mass halo, right? It cannot be a 10 to the 7 solar mass halo. It has to be fairly massive. It is also not enormous. It's not 10 to the 12 solar mass halo, which is around here. Okay, so to me, the idea, the fact that this kind of falls more or less within this gray band is remarkable, right? It really is. One should learn to celebrate. I mean, I know you guys are from Spain. You can't beat Cape Verde. But, we are from Argentina. We celebrate. Every goal we make is like, the end of the world. So this actually works quite well, right? So things to learn, and maybe we should head better and defend better, but celebrate the things that come out right? This was a prediction that can tell you, go to the 1996 paper, plot this line. It's exactly the same line, right? So to me, this is actually quite remarkable. The fact that it more or less seems to work. Now, you have other questions which I've forgotten, but it's about, sorry, remind this. Oh yeah, so the mass is not, but what do people that work on this IDM, models and stuff say about this? Well, I think it's pretty obvious that the old ideas for SIDM, the ideas were introduced to explain the cusp versus core problem in dwarf irregulars. Haven't talked about this, so forget it. For those of you who don't know, were introduced because of that. They were introduced actually because they want to fit things in Fornax, for example. And that's why the numbers that come out here, I'm not sure what that is. Or 10 to the 7. People want to explain the mean density of Fornax. That is clearly ruled out. That cannot be like that. Okay, so we may be doing many, many things that are wrong. Giuseppina may be right about something, but I don't think these velocities will go away completely. I'm not sure these are all basically 0. Okay. So there's still a bit to learn here. Aerobars need to be tightened, etc. But I think the fact that these things are much denser than 10 to the 7 is pretty well established. Now, people in the SIDM community have turned around and said, okay, no, wait, we wanted to introduce this cross-section to make things that have a core, a constant density region. But what happens if I now turn this parameter and I make the cross-sections so high that I can overshoot? I can form a core, but very quickly I can go into gravothermal collapse, into core collapse, in which case the densities will first form a core and then they will collapse back up and end up more or less as dense as cold dark matter. And that clearly is possible in the models. Whether it's true or not, I guess still remains to be debated. It seems to be less appealing to me in the sense that you want to introduce extra parameter and make it so extreme that now you end up having the same result as with cold dark matter. Mental hygiene tells me you should make it 0, the cross-section, and it works reasonably well. But hygienic things are not always the best, not always correct. But anyway, those are my thoughts on that.
Okay, I guess we have to finish the question sessions, but we have the scientific coffee now. So if you want to continue discussing, I guess you can take as many questions as you want. So yeah, let's thank the speaker again. And just a quick reminder for the students that want their attendance to be registered, please just come here in front.
You know where? Give it to you. Okay. No, I can. I know.